Okay, it is time to begin the next session, Experiments Right or Wrong. Do I have your attention? Okay, most of you are wondering who I am. You're trying to figure out who is this historian of science who I've been spending 40 years in the field in, and I still haven't heard of him. And the answer is, I am not a historian of science. I am a professor of physics, Johns Hopkins University, and you might wonder why is it that some random physics professor from Johns Hopkins University is at a party to celebrate Jed Buchwald's 70th birthday. So, I can answer that for you. I was a professor at Caltech from 1999 to 2011. When I came here, my then wife had a research position in Diana's group, and Diana adopted us, as she has adopted many of you, I'm sure. And we became very good friends. Jed came the next year, and my wife and I split up. I now have another wife, and we remain very good friends. And I would say that my relationship with Jed and Diana is as close to family as you can be without actually being family, which is actually the best possible thing if you think about it. So I don't have any very good stories about Jed. I understand he's a very distinguished historian of science, which is, I guess, is why you're all here. I've never read any of his scholarly works. I did read the book about Newton. I read the book about Egyptology. They were very nice. I enjoyed them. But I actually don't have the type of appreciation for his contributions to the field that I'm sure you do. I do understand, and did understand from the time that I first came, that he was a very distinguished scientist because one of your colleagues, Ido Yavitz, was here on sabbatical that year, and I was hanging out with Ido quite a bit. And Jed was going to be showing up here the next year, and Ido told me that Jed is arguably the foremost historian of science in the world today. And I thought, wow, that's great. And then Jed came, and then Jed said, well, Ido, he's not really as smart as he thinks he is. And that sort of discredited Ido's credibility. And so I wasn't so sure anymore, but then with time I got to realize that what Jed was saying about Ido was, he's actually a pretty smart guy, because one thing I was going to tell you, which is no surprise to you, is that the one thing I learned from Jed about history of science is that none of you are as smart as you think you are. But I think you all know that about Jed. The other thing I tell you about Jed is my wife and I got married in 2009. And since it's California, we decided we would have a friend do the ceremony. And the obvious choices were Jed or Diana. And we discussed it for a while, and we decided to go with Diana because Jed, we noticed, when he talks, uses lots of big words that we don't understand. And fortunately, after the iPhone came out, I could be talking to Jed and be like, flatulence. Yeah, I can see what that means. So anyway, we decided to go with Diana because we thought it would be nice to have people understand what was being said at the ceremony. But I guess all of you are very erudite and probably use lots of big words. So I'm guessing that for you, Jed just talks like anybody else. I'm curious to know how many of you have officiated wedding ceremonies. Okay. Anyway. I'm very pleased to be here and honored to be invited, and happy to wish you a happy birthday, and I thought maybe we should move on. I apologize that I do not know the speakers and cannot introduce them quite as authoritatively as some of the prior chairs, but I did look up Alan Franklin online yesterday, and he seems to have done some very interesting work. Like me, he is a professor of physics, but actually is a bona fide historian of science.
Okay, thanks to Diana for inviting me. I first met Jed in the summer of 1994 when I was a visiting fellow at the Dibner. Since then, he has been my friend, my colleague, my co-author, my co-editor, and the editor of some of my work. Despite having to do all that work, he has managed to be a scholar of the highest quality. And almost invariably in doing all of these things, he has lowered my workload. As we all know, it's easier to review a good book than a bad book, and in 1995, the editors of Physics Today, for reasons known only to them, asked me, a well-known non-expert on 19th century electromagnetism, to review a book, which I did. And here's what I said. It's a good review. It's what I refer to as good review. The definition is that if it was a review of my work, I would send it to my mother. So, but sometimes, however, Jed's work has not always resulted in good news for me. In the 90s, I submitted a long paper to the archive, and Jed broke John Heilbrun's record for most comments on a paper of mine. Now, to be fair to John, the paper for the archive was twice as long as the paper for historical studies. The average number of comments per page, which I have no numerical value for except to say it was large, was the same. So now, in thinking about the theme of this conference, which is something I don't do very much, particularly the future, I have enough trouble trying to think about what I want to do next, much less what the whole field should do. I do want to make an odd suggestion, given that I'm here at the home of the Einstein Papers Project, is to suggest that we pay a little more attention to some of the people who do not make it into our books and papers, who don't appear in physics textbooks, because they can tell us a lot about the methodology of scientific practice at the time. My prime example, one of the examples is William Wilson. William Wilson, who is rarely mentioned by historians of physics, except for John Heilbrun, who pointed out that his results were shattering. They literally changed the way people thought about beta decay in the early 20th century. But his 1909 paper on the absorption of beta rays is a methodological masterpiece. I used to use it when I taught classes in philosophy of physics. So it's not to say we shouldn't devote time to the people of the great achievements, but I think we could pay a little more attention to those who don't appear in the books. And to do that, I want to talk a little bit about Francis Baily, Esquire, Fellow of the Royal Society, 4 times President of the Royal Astronomical Society in the 19th century, and a critic of Henry Cavendish, who is someone we do talk about. Now, Cavendish's measurements of the density of the Earth were a really great experimental achievement, published in 1798. As John Henry pointed out later, that this was the beginning of a new era in the measurement of small forces. Now, Baily was having none of this. Baily in 1842 stated that he wasn't even sure that Cavendish meant the experiment to actually measure the density of the Earth. He said it was only to show you an example of how you could do it. Now, if you actually read Cavendish's paper and the detailed calculations involved, that seems a slightly bizarre statement, but he was convinced that Cavendish wasn't really doing a good, he of course had more confidence in his own measurement. And indeed, let me show you a schematic of, I need to talk a little bit about Cavendish to tell you about Baily. This is the Cavendish experiment. You have 2 large masses, 2 smaller masses, attached to a torsion pendulum, and if there's a gravitational force, the pendulum will swing, and you can measure the force by how far it swings, and therefore, and from this you can determine the density of the Earth, which is in fact what Cavendish did. Here is Cavendish's actual experimental apparatus. And the one thing that Cavendish worried about, the biggest confounding effect, was the possibility of temperature gradients. He even worried that if the experimenter was in the same room with the apparatus, their body heat would change things enough, given how small the gravitational force is, that it would interfere with the measurement. So he had a way of manipulating the masses from outside the room and observing things with a telescope. That was his achievement. Again, Bailey was not impressed. Now this, he said this, so he says, Cavendish chose an outhouse in his garden at Clapham Common, and having constructed the masses within the building, he goes on. Now, I thought outhouse, in common American usage, that means privy or outdoor toilet. So a friend in the English department said, no, you have to look in the Oxford English Dictionary. It turns out to mean just any building or a barn or a shed attached to a house or on the same grounds, but it was there. Okay, now Cavendish gets an answer of 5.48 for the density of the Earth, which with the density of water being 1, so it's more dense. Bailey gets 5.67 and regards his results as far better because Bailey said he did 2,153 experiments, whereas Cavendish only did 23. Actually, Cavendish publishes 29. Bailey can't count. But Bailey had a very odd way of defining experiments. Every 4 measurements counted as an experiment. And he, for various reasons, took the last of 4 measurements as the first measurement in the next set. I'll come back to that later. He was, so, indeed, and Bailey was, as he says, very, very confident. There's evidence from the detail with which he refers to himself in the third person. This has been known to happen recently. Given of his own experience, he's just very happy with his own value. Okay? So, indeed, it turns out that Bailey does his work in 1842. In 1872, Cornu and Bay in France recalculate Bailey's results. What they said is he can't move the masses fast enough to get that 4th measurement as the first measurement in the next one. And so they took a sample of his 2,153 experiments. They took 10 and said, what happens if we throw out the first measurement? And it turns out it reduces Bailey's value from 5.67 to 5.55. I don't know why Bailey thought they were different, because Cavendish gives an uncertainty of 0.38. Okay, so indeed, in 1886, W.J. Hicks continues work. He looks at the temperature dependence of Bailey's work, which comes out to be very interesting. What he finds is that as the temperature goes up, the density goes down. There's a huge effect in Bailey's, and this is something Bailey did not notice. And given his criticism of Cavendish, this is, shall we say, ironic, that indeed there is a huge temperature effect in Bailey's work. Now, pointing, he of the famous vector, says that it's no big surprise because Bailey did his experiment with light masses in the winter and with heavy masses in the summer, although he doesn't explain why this is going to give the temperature effect. But it is certainly there. Now, there is, however, an oddity in Cavendish's result. Cavendish used two different torsion pendulums. He used one with a weak wire and one with a stiffer wire. He did use the weak wire for the first 6, the stiffer wire for the last 23. And what Cavendish says is that he got the same answer for both sets, and so he just combined them. He got 5.4. It turns out that's wrong. The average for the first 6 is 5.31. The average for the next 23 is 5.48. And I thought I was particularly brilliant by noting that if 4.88 was actually 5.88, everything is solved. That you can go, if it goes to 5.8, I said, well, maybe it was a typo, or maybe he misread it, or something like that. Well, my faith in my own brilliance was, shall we say, deflated when I discovered that Bailey had found this 175 years earlier and done me one better. Bailey not only discovered this and pointed it out, but he went back to Cavendish's published data and recalculated what the density should be, and it is 4.88. So Cavendish must have made a mistake. Now, what's interesting about this whole thing is that in almost every physics textbook, it says Cavendish measured big G, the constant in Newton's law of universal gravitation. He did not, and in the 19th century, almost nobody did. In fact, in 1894, Boys makes a plea for not measuring little g, the acceleration due to gravity, which is, after all, parochial. It's just about the Earth. You should measure G, big G, which, as he says, represents that mighty principle under the influence of which every star, planet, and satellite in the universe pursues its course. And Boyce takes his own words seriously, and indeed, in 1895, publishes a value of G. Now, what's interesting about the measurements of Cavendish and others in the 19th century is that their results do not agree. Measurements of the density of the Earth range from 4.25 to 7.6. Yeah, that's, it was in such disagreement that Poynting in 1890 is willing to do an experiment that he admits is less accurate than using a torsion pendulum. He's going to use a regular balance, and he says, look, I'm going to do this because the values do not agree. And we ought to have more measurements just in case it has something to do with the method of measurement. Now, you might say, well, this is the 19th century. They didn't have great experimental apparatus. And, that may account for why they get such different answers. But let me point out to you that this is the CODATA values of G from 2014. This is the measurements of G. Now, you will notice that the precision has increased remarkably. G is now claimed to be known to 4.5 parts in 10 to the fifth. But notice, these values don't agree. Here's one with a nice small experimental uncertainty, and here's another one. And they differ by maybe 5 standard, maybe more standard deviations. Here's another good one, Gundlach and Berkowitz. They claim to be able to measure to 14 parts in a million, and this was Quinn and company who only claimed to measure to 40 parts in a million. The only trouble is they differ by 200 parts per million. And it hasn't gotten any better. You might, on the basis of this, question whether or not there really is a universal gravitational constant. Now, I just have brought this up as an example because there has recently been a lot of discussion of the replication crisis in psychology and the other social sciences, where the Open Science Collaboration took 100 papers from 3 leading psychology journals, and they expected to replicate 90%, and depending on what criterion you use, they only got 37% or 49%. And this has been regarded as a crisis, and I just want to point out for those of us in physics that we aren't necessarily morally or instrumentally superior. And it might be interesting to look at the history of some of this kind of discrepancy in measurements. Fortunately, if you want to do this, there's a marvelous book by Arthur Stanley Mackenzie written in 1900, that gives descriptions of all of these experiments. I haven't looked at all of them yet. I don't know if I will. That's the future of my field. And so I do want to congratulate Jed on his 70th birthday. He's a baby compared to me.